Let's start with 3D sharing. If you can recall sharing in 2 dimensions, it looked something like this. This was your 2-dimensional space. Then you had a 2D object onto which you can apply sharing transformation either in the x direction or along the y direction. If you have applied shearing force along the x direction, you can recall that changes take place on the y coordinate values, and if you have applied in the y direction, then there was no change in x-axis values, and the changes happened only in the y coordinate values. Now that means, to grab the concept of sharing in 2-dimensional space, you had to decompose the task of sharing into 2 parts. One was x-axis sharing and another was y-axis sharing. In 3-dimensional space, the concept is much similar, as there are 3 primary axes, there is x, y and z. You have to decompose your sharing task into 3 parts, namely sharing along x-axis, sharing along y-axis and sharing along z-axis. Now let me dive deeper into the mathematical equations. If you apply sharing along x-axis, then x coordinate values actually don't change. Only change occurs in the y and z coordinates, and mathematically it will look like this. So assumption is that before you apply sharing transformation, your original coordinate values are x0, y0 and z0, and SHY and SHZ are the sharing transformation factors for y and z coordinates. So as we have looked that once you apply sharing along x-axis, only the y and z coordinate values will be changed by their corresponding sharing factors. The equations will be like this. There will be no change in x coordinate value, hence x1 equals to x0. There will be change in y coordinate value like this. y1 equals to y0 plus SHY multiplied with x0 and z1. That means z coordinate value after sharing transformation along x-axis equals to z0 plus SHZ multiplied with x0. Now if you want to convert this into a single equation involving homogeneous coordinate, you have to append homogeneous 1 equals to 1, and your entire set of equation will be like this once you convert this into matrix form. So this is your sharing matrix along x-axis. Sharing matrix along x-axis in 3D. Just take a note of this. Now let me look into sharing along y-axis. In this case, what will happen is there will be no change in y axis or y coordinate value. Changes will take place only in x and z coordinates. So once you apply shearing transformation along x-axis, your equations become something like this: x1 equals to x0 plus shx multiplied with y0, y1 equals to y0, no change in y coordinate value, z1 equals to z0 plus shz multiplied with y0. So just observe this set of equations, how the changes are taking place, and if you convert this to homogeneous matrix equation by appending 1 equals to 1, then you get something like this: vector x1 y1 z1 1 equals to, this is your shearing matrix along y-axis. Shearing matrix along y-axis. There you go. Now the third portion is shearing along with z-axis. Now when you apply shearing transformation along z-axis, what happens? Like the previous two instances, there will be no change in z coordinate value. Changes will take place along x and y axis by a factor of original z coordinate value. Have a deeper look into the equation set. x1 equals to x0 plus, and this is the portion of the change which will take place into the x coordinate value by a factor of z coordinate value, is hx multiplied with z0. Similarly, y1 equals to y0 plus is hy multiplied with z0, and there will be no change in z coordinate value. Now if you want to convert the set of equations into homogeneous system, you have to append the homogeneous 1 equals to 1, and this is going to be your equation in matrix format. So this is your shearing transformation matrix along z-axis. So in 3D you can represent shearing transformation using these three matrices. Shearing, it is on. Something is wrong here. Just wait a second. Yes, it's here. You can represent shearing in 3D by using three matrices. Shearing matrix along x-axis, where it is. Then using shearing matrix along y-axis, here it is. And lastly, shearing matrix along z-axis, here it is. Now this was shearing list look at now rotation about an arbitrary axis in 3D. So in 2D, if you can recall, rotation used to take place with respect to the origin or by some arbitrary point. So if you had to rotate something with respect to this arbitrary point P, what you had to do? First you had to translate this point P to the origin, then you had to apply rotation with respect to the origin, then again you had to translate everything back at their original location by applying a reverse translation of the first one. Now in 3 dimensions, what happens? You know from our study of rotation in 3D that rotation can take place with respect to primary axis, which are essentially lines. So in 3D, rotation can take place with respect to some arbitrary line. So just imagine of this vehicle, it should be horizontal to the ground, or it should be grounded properly. Now look into this red line. If you use this red line as a screw, or suppose this red line is like a chassis which is passing through this vehicle, and you are strong enough to rotate the entire vehicle by turning this red line as a screw following this black arc which I have drawn right now. So once you turn this as a screw, your vehicle will be rotated like this, as you can see into the diagram. So this line basically is not belong to any of your primary axis. You cannot think of this as a x-axis or any y-axis or z-axis. This is an arbitrary line. So in 3D, rotation about an arbitrary line or arbitrary axis is possible. However, the problem is that there will be some long sequence of mathematical operations. So just have a brief look at the sequence of mathematical operations. If you understand them, then you can apply them in algorithm. So let's start. Before that, just let we go back to our Blender software. This is your green line, is your y-axis. This red line, you can see it here, is your x-axis, and your, where is my pencil? Yes. Z-axis should be something like this. So this is your z-axis. You can see the z-axis is the vertical one. Your z-axis should look like something like this. So what is an arbitrary line? So now, before, what we used to do is, you used to do the rotation by this this primary axis systems. For our 3 rotation matrices, we used this primary x, y or z axis as screws. Now you have an arbitrary axis, which is nothing but a line in your 3D space. Say this is the arbitrary line by which you have to rotate some point which is located in your three-dimensional space. So our rotation matrices are established with respect to the primary axis, as well as the assumption is that rotation is done with respect to the origin. So first thing what you have to do is you have to shift this arbitrary line, which for the time being is not passing through the origin, to the origin. That means you have to shift this line somehow so that it passes through the origin. That means the transformation you need to apply onto this line is translation, so that this passes through the origin. For the sake of simplicity, let me move this object. Not able to move it. Leave it. Achha. So if you apply a translation such that this line passes through the origin, now your line will be like this. Say it is L dash. So first step you have applied is translation. Then next step is to align this line with some of the or any of the primary axis. To do this, first what you have to do, you have to push this line onto some primary plane. You have three primary planes: xy plane, yz plane, or xz plane. You have to push this line so that it will lie on some primary plane. Now you can see that at this position it is not lying on any of the primary planes, any of the three primary planes. So if you push it like this, your line will be passing through the origin and will lie onto some primary plane, say onto the yes, like this. Now you can see that this line is lying onto the primary plane xy. Next step will be, so you can achieve this lying onto the primary plane by rotating this line L by an angle the line is making with this primary plane. You can see that this line L dash is making some angle with the primary plane xy. If you rotate this line L dash by an angle or by that angle, it will be onto the primary plane xy. Now your next task will be to align this line L double dash with your primary axis, say x-axis. For that you have to find the angle of the line L double dash with the primary axis x-axis. And if you rotate this line L double dash by that angle, now your line will be aligned with the x-axis. Now what you have to do? You have to do the actual task of rotation with respect to x-axis. Now you have the rotated point, but it is not at the place where it should be. So what you should do? You should again do a rotation so that line triple dash or entire system is transformed to with respect to L double dash. That means a reverse rotation. Then again you need to rotate your entire system by this angle, but this time in the reverse direction, so that entire system is transformed to the system which is defined by this L dash. Now lastly you have to do the reverse translation to put everything back with respect to L. So now I believe that you know the sequence of the operations. Let we look at the mathematical things briefly. First, you can define the line L by a vector xyz. So this is basically nothing but vectorization of a point on the line. So how it goes, like x equals to au plus x0. X0 is the x coordinate of this starting point p0. Y equals to bu plus y0. Z equals to cu plus z0. And what is u? U is your directional coefficient, and if you represent a line in vector form, it looks like something like this. And a b c is basically the x distance, y distance and z distance of a point from the origin. So your line L can be represented something like this. Root under s square plus b square plus c square u. So in another words, you can say that this length from P0 to P1 is defined by this value. This is simple geometric phenomena. If you give it some thought, you can understand it. So this distance is basically a square plus c square root over. Next, as we have discussed before some time, first you have to translate everything so that your arbitrary axis, that means in this case the line L, passes through the origin, and it can be achieved by this translation matrix. So the distance from origin O to P0, or in simple terms, the coordinate for point P0 is x0, y0 and z0. So if you translate this line by this minus x0, minus y0 and minus z0, then your line is going to be passed through the origin. Next, as we have discussed, you have to push this line or translated line so that it lies on the xy plane. You can figure out the xy plane here. So for that, what you have to do, you have to find the angle this line L is making with the xy plane. So from observation you can find it out. How? this distance is L, right? And so can you figure out this vertical distance? Yes, this is C. Sorry. Right? So, from this simple thing, you can find this angle. How? So, if you think of this as a triangle, let me draw the triangle in 3D space. So, this distance is going to be root under b square plus c square. So in simple terms, if you try to find the sine theta and cos theta, say this this angle is theta. After pushing this line should be somewhere here. Your sine theta will be b over v, and cos theta 1 will be c over v. So if you rotate everything by this rotation angle, you will get your line onto this xy plane. Next, the diagram is not clear here. You have to rotate this line, which is now on your xy plane, say by an angle phi, so that it gets aligned with the x-axis. So for that, say this angle as per the definition is not phi, it is theta 2. So if you observe a little bit, theta 2 is going to be sine theta 2 is going to be minus a over L. L is the length of the line, and cos theta 2 is going to be v over L. V, this is v. So this is the second rotation which you need to apply onto your system or in your mathematical sequence, so that your arbitrary axis get aligned with the primary x-axis. Then simple rotation with respect to x-axis. Now the main rotation task is complete at the step 4. Now next task will be to reverse this rotation, in which we have aligned our arbitrary axis along with the x-axis. So for this, you need to rotate everything by an angle of minus theta 2. So this is going to be your rotation matrix. Then you need to rotate everything so that you get to this position, the position at which you have arrived after translation, so that your arbitrary axis passes through the origin. So in this case, your angle of rotation should be minus theta 1. This is going to be a rotation matrix. Lastly, you need to translate everything back so that you get your arbitrary axis back where it actually used to be. That means here. That means you need to apply a rotation by x0, y0 and z0. So this was the sequence of operations you need to apply if you want to rotate anything with respect to some arbitrary line. Just try to remember the steps, and this mathematical operations are a bit complicated, so give them your thought if you are interested. That was rotation about arbitrary axis, and here is your complete sequence of operations. Here you have an example onto which you can apply the mathematical formulas. And lastly, a disclaimer: this slide is not made by me, it has been copied from the internet. So that's the end of the tutorial portion.